Okay, so, what? Sorry,
Are
what?
these ever accessible to us? Like your
What?
PowerPoints and stuff?
Oh, I mean, I guess so. I haven't like shared them on Canvas or anything, but I could try to figure that out. If you want
I was
to.
just curious. No pressure.
No, you should put them on.
But it would be baller.
So, we're going to talk about computers today. And you're like, Jason, I know about computers. And no, you don't.
Okay.
You don't know about computers.
Sure.
We're gonna like start explaining this to you, so you really understand it, okay? Because it's important. You really got to understand it. The computer, it does everything for us now. So, what do computers do? Well, a lot of what I'm going to share with you today is kind of something I adapted from a computer science book called Computer Confluence by George Beekman. I like the way that he sort of explained this. So if you like this, if this is like really interesting to you, check out that book because a lot of this is adapted from there. So, okay, what does a computer do? Yes. It's kind of an old book, but very good. Okay, got it? Okay, so what does a computer do? Well, computers do 4 things. And that's it. And the 4 things that computers do are input, output, processing, and storage. That's it. That's what a computer does. Everything that a computer does can fall into one of those 4 categories. Input, output, processing, storage. I want to talk about each of those. Okay? So let's start by talking about input. So input is when a computer accepts information from the outside world. Now, it can collect that information from other computers, or it can communicate, or it can collect information from you, the user. And if it's going to get information from the user, it gets that through different input devices like, a keyboard or a mouse or a camera, a microphone. So these are input devices that allow you to communicate information into the computer. And if the computer is going to collect information from other computers, it's going to do that probably over various network protocols or wireless, Bluetooth, stuff like that. Those are the ways that computers talk to computers.
What would it fall under if you're using like a Bluetooth mouse or something?
Well, yeah, so like that's what this is. So like the mouse is collecting the information from me, and the mouse is actually now a little computer. And so, because the mouse has its own input-output kind of capabilities and some processing and storage capabilities. So this is actually a little computer now. And so the mouse talks to the computer. So technically the computer is collecting information from the mouse, and the mouse is collecting information from you, right? So there's a little bit of a piggyback going on there.
Everything is computers.
Yeah. Everything is computer. Okay.
Nothing is computers.
All right, let's look at output. Output is just the opposite. Output is the way that the computer communicates to the outside world. And the computer can communicate information to other computers, or it can communicate information to you, the person, the end user. The computer communicates to you through output devices, like the display monitor, or a printer, or a loudspeaker, or I don't know, what are some other output devices?
Fax machine.
Yeah, maybe.
Wait, why'd that one get that response?
But these are the main ways. The computer tells you things by letting you hear something through the speaker, or letting you see something on the screen, or back in the olden times, we would have to print it on a piece of paper in order to get the information. The thing is, the computers don't talk to the fax machine. That's the problem.
Oh, yeah, because it's got a number, doesn't it?
Yeah, it's just a telephone thing.
Oh, I forgot about that.
That was weird.
Although there used to be things called fax modems that you could put in a computer,
Uh-huh.
and the computer kind of became a a virtual fax machine.
Oh, so when you would get faxes, they would show up as like a little notes thing or like
Yeah.
a physical. That's cute.
Yeah.
I like that. Why did we get rid of fax machines?
I don't know, they were cool. Okay. So processing is where the computer basically does math. Okay, so the computer can perform arithmetic or logic operations on bits of information. And by logic operations, I mean like decision making. You can make decisions. And that is done with something called a CPU, which we'll talk about in a minute, Central Processing Unit. Okay, so this is the main work of the computer. You know, when we think of like the computer doing work, this is what we're talking about, is computer doing math, or logic, or both, usually. Computers are really good at math and really good at logic. They're really good and really fast at those things. Whereas human beings are typically not very good and not very fast at arithmetic and logic. We can do it, but the computer can do it way better than we can, way faster. All right, storage. Storage is how the computer kind of like moves and stores information around inside of the computer. So as it collects information from us or from computers to the input devices, it has to put that information somewhere while it's working on it and doing math on it and making decisions about it. And so it has to have some ability to store that information while it's working on it before it sends it back out. There are two main kinds of storage. There's primary storage and secondary storage. Primary storage is things like RAM, which is there's some RAM.
You should check out his brain.
That's a one little sticker.
Oh, yeah.
How much RAM is in that RAM?
Actually.
Oh.
This is 2 gigabytes of RAM in this one little stick.
Yeah.
Oh, that's so little, but it's so big.
So 8 total?
Like, that's
Well, I've got another one here though.
how old is this computer?
Oh, I don't know.
1 million years old.
That old.
Well, it's like I feel like they sell RAM sticks for like 4 million terabytes, and it's like this tiny little.
Special now.
It says
Yeah.
2007.
Most of this is heat sink.
Oh.
The actual RAM is just this tiny little
Yeah.
brick in the middle. But anyway, so RAM, okay? RAM is considered the primary storage device of the computer. And the important thing to know about that is it has to be really fast, because this is where the computer stores the information that it needs instant access to. So the RAM is super fast. It stores the data as a pattern of electrical current. And electrical current, you might remember, is like the energy in motion, right? So you've got electricity moving across these chips, and the data is kind of like stored in a pattern as on top of that, you know. Which means it's really fast. You can pull that information in and out really quickly and do things with it really quickly, because it's just electricity, and electricity is pretty fast. The downside to RAM is that it's really volatile, meaning like if it forgets forever. Like there's no like recovery if that electrical signal gets interrupted or something, like whatever was on that RAM stick is just gone. And there's no getting it back. So you're trading off kind of speed and long-term reliability here. So in the effort to get it really fast, you sort of have to give up on, you know, really reliable retention of that data. But remember, the computer is really fast, and it only needs to store this information for tiny little bits of time while it does math on it. So that's totally fine to have it on RAM.
What like math is it doing on it?
It depends. We'll talk more about that, but basically the processor is just a whole bunch of transistors. and the transistor can have a 0 or 1 state, an on or off state. And so what it's really doing is just like flipping transistors back and forth. And so if you can, there was this, in the 19th century, there was this guy named Charles Babbage who invented this machine called the analytical engine.
Oh, and then.
And it was basically a mechanical calculator. And he never really got it to work, but it basically was a binary calculator, okay? But it was mechanical, like it literally was like levers and switches and stuff. And he was just trying to make a calculator that he thought was cool. But then there was this woman, Ada Lovelace, who came around, and she like looked at it, and she was like, wait a minute, like you can make that do anything. And so she ended up writing a lot of papers about this, and she's kind of credited as kind of the world's first computer scientist.
I love her.
And
Sorry.
she, there's this great quote from her, it might even be in this, I know it's in my book, but I don't think it's in this presentation, but it might be, where she kind of said, you know, basically the computer can do anything that you can teach it to do, as long as whatever you want it to do can be distilled down to binary language that you can do math on. As long as you can do that, then the computer can do anything. So what kind of math is it doing? Well, it depends. It depends on what you want it to do. But in our case, in sound, like we have to distill sound down to zeros and ones, and then figure out what math we need to do on it to get the result we want. For example, if we want to make the sound louder, we have to do the kind of math that multiplies the amplitude that is represented by those zeros and ones. So it just depends. But it took a while, actually, for, I mean, Ada Lovelace she was thinking like way ahead of her time. And it took a good while for everyone else to kind of catch up to what she was saying, because a lot of people didn't really understand it. They were like, I don't get what you're saying. But we got there. And she was totally right, like completely right about everything. And so very cool. You should go read some of her stuff. It's really fascinating. So anyway, the other kind of storage is called secondary storage, and this is like long-term storage. These are things like hard drives. Like there's a hard drive. Okay, hard drive can hang on to stuff for a really long time. These days, you know, we still have hard drives, but we also have solid-state disks. We talked more about this, you know, in December. But secondary storage are storage devices that can hold on to the information for extended periods of time, you know, theoretically forever, absent any, you know, tragic interactions or anything. But it'll hold on for a while at least. The trade-off there is they're slow. You know, comparatively speaking, compared to RAM, these hard drives and SSDs and stuff are slow. Although the SSDs are getting pretty fast. Not as fast as the RAM yet, but getting close, actually, compared to where we used to be, which is cool. All right, so all that in mind, this is the system diagram for every computer ever made. Every computer you have ever interacted with your life, this is the system diagram for it. So every computer will have some amount of input devices that collect information in various ways, and some amount of output devices that collect information in various ways. They will have some kind of primary storage, or RAM, and some kind of secondary storage, and all of that gets shuttled around inside the CPU, the processor, the central processing unit. That's the CPU.
It's big.
Just throw 'em around.
so little.
So let's talk about the CPU, Central Processing Unit. So every computer has at least one of these, or it's not a computer. Can't be a computer without a CPU. The CPU performs math and logic operations, and it communicates with all the other parts of the computer. And it sits along with a bunch of other chips on some kind of circuit board. Now this particular computer has 2 of those in it. And I'm pretty sure each of those chips actually has multiple processors inside it. That was a thing we started doing in the early 2000s, was like, we kind of hit the limit of how fast we could make the chips run, and so we just started putting more into them. It was like, well, we can't make it go any faster, but we can double the amount of them we have, or triple the amount of them we have. Yeah.
What do the numbers mean on the boxes? Yeah. Like it has, did you say the
At least I thought so.
Yeah.
It could just be like nothing.
I don't know.
What? Sorry, I don't think I get that.
Hi,
Imagine being in that meeting. It's like, guys, we don't know how to make it
Oh.
faster.
Yeah, like on the little bits.
Oh, well, those are just like part
Oh my
members.
God,
I
is
just
that-
think about it all the time.
I mean, that would be cool.
Live
too.
use of
Yeah.
the magnifying glass.
Yeah.
Yes, dude.
Anybody else need to look at it?
I want to.
So we're on this like endless chase to make these things faster. Because the faster we can make them, the faster they'll do work for us. I watched this really interesting video the other day, actually, that was just so cool, which was basically we're to the point now where making them faster is about making the transistors smaller. Because the smaller we can make the transistor, the shorter the jump is to flip it, and therefore it flips faster.
Huh.
These are the little, they look like candy.
Yeah, kind of. And so
I don't remember.
I don't know why.
it's like,
I think if you're thinking
Resistors maybe look a little more like candy. than
oh,
candy.
resistors. No, transistors. Transistors.
good for them.
So anyway, it was a really interesting video about like the way that these transistors get like put into these tiny little chips involves light, really shortwave light, and
Big transistor.
and the video was about this company that like figured out a way to do it with ultraviolet wavelengths, which is crazy, like so beyond crazy, like what they had to go through to figure this out. They basically had to figure out how to create a tiny little sun inside of a box.
Which I'm sure has no ramifications.
No,
at all.
none at all. It was not hard at all, even. It's not like it took them 40 years or anything to figure it out. But yeah, it's so wild. And so this is what we're doing, is we're just trying to make it smaller and smaller. So the smaller we can make them, you know, and they're so small now, like you literally need a microscope to see them. Yeah,
How many transistors are we up to?
billions,
Yeah, okay, that's what.
billions on that little chip.
Yeah.
In there?
Yep.
Yeah.
What the fuck?
Yeah, well, that's the one you were looking at is a big one.
Oh,
We
okay.
put a lot of really little, very, very little tiny little resistors.
I always love looking at
Billions
them.
in there?
Yeah.
What are we doing, guys?
Yeah.
We're doing transistors.
And I could just like stab it.
Yes, let me just see the transistors.
Yes.
Jason, you got that magnifying glass again?
Yeah, you literally need a microscope. And there's also layers to these things, like they're so small that there's like,
They can stack it.
yeah, they're stacked in layers and things, and so like you also need a microscope that can penetrate like surface area to see them.
So how do they mass produce these?
Yeah, what the?
I'll send you this video. It's like,
Actually,
it is
Yeah, put that
just
on
like
Canvas.
wild. Yeah, I'll put it on Canvas. I mean, honestly, just as a heads up, like, I barely understood this video.
That's how you know it's good.
That's good.
Like,
I didn't know what they looked
It's
like.
about
so.
this thing's about an hour long, and I watched it this weekend, and I was like,
Right.
I am understanding what they're saying, but like, only barely. You know,
Learning.
about half of the things that they were talking about are just like, I think I get that, but I don't know. I'm going to take that on faith. You know, it's just mind blowing. So anyway, you need these, and you need them to be fast. So when you're thinking about a computer, a CPU, aside from the things we were just talking about, if we climb back up the abstraction layer ladder a little bit, and look at the bigger picture, you're primarily concerned about these two things: compatibility and speed. Okay, so for compatibility, not all software is compatible with every CPU. So CPUs are generally designed in families. And the family is sort of like there's an underlying architecture for how that chip does the math that it does. And each of them do it a little bit differently. And there's, pros and cons to each approach. But, for example, there's a class of CPUs called ARM processors, and then there's a type called x86 processors, and they're not compatible with each other. You can't run apps on one that were designed for the other. Yeah.
Is this like, that's just how the technology is, or is this a big computer thing? Like, are they trying to be like, no, you have to buy ours? Or is it like, just the technology doesn't?
Yeah, it's a little bit of both. I mean, if your thing doesn't do anything differently than the other person's thing, then why would someone buy your thing? So there's a little bit of like ours is different so that it's different. But it's different for other reasons too. I mean, there are some benefits. I mean, for example, Apple was using Intel processors in their computers up until 2000 or so, or 2020, and then they switched to these their own processors that are ARM based, and it's just a very different architecture. But that switching to that architecture allowed Apple to make a huge leap in performance. Like they were able to leverage that difference in a way that just like shot their performance levels through the roof, in a way that they hadn't been able to achieve before with the x86 processors, or it was going to be harder for them to achieve. Because part of what's happening is it's all about power now. And by power I mean like electricity. Because everybody wants longer battery life, and to make these little like literal, I mean it's like not literal, but it's like when you look at these chips under a microscope, it's like it's a city is on that chip, like a huge metropolis city is on that chip, full of like buildings full of chips and transistors and miniature things. And to get all that work, you're pumping so much energy into those things because there's so much on there. It looks like it's a tiny little chip, but there's like so much in there, and it needs so much energy to do what it's doing. And not all that energy gets used to do work. A lot of it just generates heat. And so there's an efficiency problem there that they're constantly battling, of the performance per watt kind of factor. And so a big thing that Apple got by switching to that ARM architecture was that performance by watt thing got really good for them. Battery life got really good. They were able to optimize some other things because of that. So there's some benefits to each thing, but yeah, some of it is just like, which one do you want to use? But some of it is a scale factor in terms of like how big is the thing you're trying to make, you know, or how little is the thing you're trying to make, and different architectures work better for different kind of sizes or different types of processing that you want to do. But whichever one you decide to use, that is going to dictate what kind of software you can run, because not all software can run on every computer, except for when you write software to make the software work, which is all the rage these days now. So,
That confused me.
so you've got a piece of software that is not compatible with a certain kind of chip, right? Well, you could write a piece of software that is compatible with that chip. That's only job is to translate this software into instructions that this chip can understand, and vice versa. It's just a decoder ring, basically. You take a performance hit to do that, because that's now, you know, the CPU is now doing a bunch of work it shouldn't have to do just to translate all the commands. But the app runs, so it runs slower, but it runs. And this is what's happening when you do things like run Parallels or VMware on your Mac that lets you run Windows on your Mac. Like, that's what's happening. Is Parallels is a piece of software that is translating the machine code to allow that Windows software to run on your Mac CPU. Okay. Okay, speed. So you want the CPU to be fast. And, you know, one determining factor of the computer speed is what's called its internal clock. And this is like, you know, how many times per second can it do math or make a decision. But this clock, because of this architecture issue, the clock has kind of become a little misleading. It used to be like that's all we really cared about. But then we kind of hit the limit. But yeah, like a 5.4 gigahertz Intel Core i7 is not necessarily faster than a 4.05 gigahertz Apple M3 Max processor. The Apple M3 Max technically has a slower clock speed, but its architecture is quite a bit different than that Core i7. And under certain circumstances and in the right kind of system with the right kind of software, that M3 could run faster. Like in terms of like the amount of work it could get done, it could be more. Yeah, Ken.
So does that mean that there are other like computers that wouldn't be able to run specific softwares because their clock is also out of sync with that one?
Not necessarily. I mean, there is a little bit. You know, some software, especially in sound, things like sound that are time dependent. Like, you know, your CPU has to be a certain amount of speed in order to just be able to do the work fast enough. So yeah.
Is giga a million? So 4 million times a second?
Yeah.
Okay.
So.
Not up to speed on my metric conversion.
So it's a lot. I mean, that's really fast. 4 million decisions and or math problems every second is like pretty fast.
I just think you could do that.
But you know, we'd always like it to be faster. So when I say that architecture is really the important thing, like, so maybe, you know, one of the ways that these two processors are different is that, like, that Apple M3 actually has multiple processing cores in it, and it has two different kinds. It has some processors that are designed to be really energy efficient, and then it has others that are designed to be like really, really fast, but not as energy efficient. And so the software, depending on what it has to do, can decide which processing core is on that chip to direct that information to based on the kind of work it needs to get done. And the more it can direct to those efficiency cores, the less energy it's using, and therefore the more energy it can redirect to the performance cores to do the really heavy work. without draining your battery or something, you know. So there's a lot that goes into this. But understanding that there is some concept of speed that is important to you. That's the thing that decides how many tracks of audio you can have at one time, how many plugins you can run at one time. You know, the speed of that processor is a big part of that. Okay. But also there's things like how big of numbers can this chip look at one time? You know, there's 32-bit processors and there's 64-bit processors. And a processor that can look at a much bigger number could do certain kinds of math faster than a processor that can only look at a 32-bit number. You know, that 32-bit processor in most cases could do the same math, it just would be a little harder. And so it would be slower. So it just kind of depends. Yeah.
Is it this internal clock is where overclocking comes in
Yeah.
when you push your computer to do stuff
Yeah.
that
So
it
sometimes
wasn't made for?
we don't really do a whole lot of this anymore because the processors have just got a heck of a lot more complicated. But yeah, back in the day, all the rage was like trying to get that CPU to run a little faster. Because the whole idea is the chip maker will make the chip, and then they'll try to see like how fast can they push it before they cross that heat to performance ratio, where it's generating more heat than it is work. And then they kind of back that off a little bit, and they say, all right, this is the speed it can reliably run. And what would happen is like the motherboard that you stick that chip on can theoretically run several different kinds of processors on it, and you just have to like set some dip switches or something to tell it what kind of thing you put in there, and then it'll run at the right speed. And a lot of people that liked to hack around with computers, like me, I used to do this. It was fun to open up the computer and like move those dip switches around and try to move that processor a little bit faster. And it'll try. It'll try really hard. And if you screw it up, like you could melt it, and then you got to get a new one.
You know, there's a whole culture around like the cooling
Oh, yeah.
aspect of it.
So this is the cooling mechanism for that chip.
It looks like a business.
This
building.
sucker is liquid cooling. Yeah, there's like coolant in that pipe. It cycles around through here.
Where does this sit?
It sits up against there. And this draws all that heat out across that liquid thing.
What are your thoughts on the liquid like piping stuff, where it like it's more of a aesthetic thing nowadays, but like people used to have that and then they would connect it to like pipes around their computer so that it'd like flow around their computer and it's like a whole thing. Just thinking about it.
I don't know. I remember the first time that I had a computer that had liquid cooling in it, I was like, is this a good idea?
Let's put liquid in the
Right.
computer.
Yeah.
Water next to it.
Like we're literally putting like a little tiny car radiator inside of this thing now to keep it cool. But it works. But you can see the problem we were up against. Like this computer was like at the height of that limit we hit in terms of like clock speed. Yeah.
What, isn't it weird?
So
yeah.
I'm pretty sure this is like a 3 gigahertz
It's always
PowerPC processor, and they just couldn't get these to run any faster than that. Like it's just like they couldn't get them to go any faster because they just kept getting so dang hot. And because this is where they were. To do 3 gigahertz, they had to strap something like this onto
Why
it.
didn't they just make it bigger?
And Apple wanted to make a phone,
Oh. Oh.
Right.
right?
That
Like her
insert
hand
sound in there.
And they wanted the phone to run just as fast as this.
Yeah, I could take.
And it was just
Yeah, I
like,
could take a little
they
bit.
couldn't do it with this technology.
Just have your phone be hot.
So they had to go to different processing technology because it's just like nobody was going to carry around a liquid cooled heat sink in their pocket.
I would have.
I was gonna say Ace.
I would have been like, check it, boom, you know.
They should just
Oh, no,
install
my
a
liquid
small
coolant.
little
How's
AC
this attached?
compressor in
Like
there.
glue? You just like rip it off.
No, it's called a thermal paste.
Right.
It's just like allows the heat to transfer between the chip and the cooler a little more
Fancy
efficiently.
fluid.
Yeah.
It's gross. It looks like the goo from SpongeBob where he makes like the Krabby Patties out of it.
Ew.
Alright.
Oh,
All right. So, a little bit more about the CPU. The CPU's job is to follow instructions. That's what it does. It follows instructions that are encoded in things called programs. And each CPU can it can only handle one instruction and a few pieces of information at a time. And that sounds kind of limiting, right? But remember, it can do this
4 million
millions
times.
of times a second. And so, like, doing one thing at a time, it sounds slow unless your one thing at a time is 4 million times a second. And then you put multiple CPUs onto one chip, and now you've got 10 of them that can each only do one thing at a time, but that one thing at a time is 4 million times a second times 10 chips. Now you're doing 40 million things a second if you can write the right kind of instructions to handle that kind of that processing capacity, and then you really got something now, right? But because of this, because there's that limitation of, well, it can only do one thing at a time, the computer needs a place to store the program and the information it's working with until it's ready for it. And it has to like queue things up. Like, you know, there's a line that forms, you know, behind the CPU where, you know, the little operations get fed into it one at a time. And that little line that all the data gets up is that's what the RAM does, the primary storage or the memory. That's where the instructions kind of line up to be processed. RAM stands for Random Access Memory. It's very temporary storage, and it stores it in a pattern of electrical current. I've talked a lot about this already. There's another kind of memory called ROM, which is read-only memory. And this is a storage device that the computer can never write information to. Like, it can never save anything to this location. It can only read from it. And all computers have some kind of ROM in it. And this contains just the most basic information it needs to start doing anything. It's like you turn it on and the chip is like, hello, you are a computer. And then it says, look here for your next instruction. That's basically what's in the ROM. Yeah.
So, if it can't write anything to the ROM, how does the ROM get the stuff on when you first plug it in?
Well, that's not how it works, actually. You have to, in a factory, they have to like burn that data onto that ROM chip.
Okay, so it's more like the storage rather than RAM. Like, it's not on a loop
Yeah,
of
but it's still
electricity.
considered primary storage
Okay.
because it's the computer's not saving anything there.
Right.
Like that is the first. That's like the fast pass line for all of the data. Like, that's where it looks first for instructions, and it gets through those instructions really quickly. And now it's like, okay, and now I'm ready to do more. It's like, well, I can only put so many instructions on that ROM chip, and the rest of the instructions are over here. Okay.
Wait, everything goes through the ROM at some point?
No.
Okay.
No, it's just
when it starts.
yeah. And then you usually have something called EPROM, or something like it. And this is like ROM, but you can change it. So it's called erasable programmable read-only memory. And this is because, like, you know, the problem with ROM is you only get one shot at it. You know, you get one chance to burn that data onto that chip. And if you have a mistake in that data, you can't redo it. You have to throw the chip away and make a new one. And so you don't really want to put too much information on that. You only just want to put the bare basic information you need to get the computer started. And then you want to send it to this other place that you can adjust those instructions a little bit. So, for example, maybe you this is the graphics card.
It's so small.
This is the card that allows the computer to display things on the monitor for you. Okay. Well, you have to tell the computer how to talk to this thing. Okay, and the computer has to know how to do that. And sometimes you would put that information in something called firmware. Okay, and a firmware is sometimes stored in something like EEPROM. The idea there is okay, here's some core instructions of how to talk to another piece of hardware in this system. But maybe I ship this thing out and we start putting it in computers. And then we think of a better way to do it. Hey, we can make this thing work a little bit faster if we tweak the instructions like this. We could make it do a few more pixels on the screen. Or we kind of made a mistake and we realize now that there was a little bug. There's a certain scenario where those instructions wouldn't work, and we just never replicated that scenario in any of our tests. But once we sent it out to 1 million people, there were 3 people that managed to replicate this very specific scenario that makes this thing not work. And what do you do at that point? Do you make everybody send these back so that you can burn new information onto it? And that'd be really crazy. So it's much easier if you can send out a little piece of data that they can go and put and reprogram that EEPROM chip or whatever it's using with new information. So if you've ever done a firmware update on a computer or some other piece of technology, that's what you're doing.
What's the difference between a firmware update and a driver update? When there's a new driver that comes out that you need.
So yeah, a driver is a thing that tells the operating system how to communicate with a piece of hardware.
Okay.
The firmware is usually about hardware talking to hardware.
Okay.
So it's a little bit different. We'll get into operating system in a minute. Okay, so secondary storage devices. Your options. You have a lot more options here. You can do it magnetically. And that's kind of how hard drives work, is you're magnetizing little particles. Dude. Okay. So here's the hard drive I've taken apart. So if you looked at this under a microscope, you'd see there's little flecks of metal all over this thing. It can be magnetized or not magnetized, and that's how you get your zeros and ones. And magnetic is the way we were doing this for a long time. That's how hard drives work, that's how floppy disks work, that's how tapes work, cassette tapes, reel-to-reel tapes, magnetic, right? And if you're careful with that and store it properly and everything, magnetism can stick around for a long time, really long time. The problem with magnetic storage is it usually also involves some mechanical mechanisms to move things around, and moving parts break. So for this thing, the moving part is this little wand that has to move back and forth, or the motor that spins this thing. So the plate itself is pretty robust and hard to mess up, but that motor isn't going to spin forever, and that little arm isn't going to move forever. Yeah.
Is it kind of like on the samples where they only have so many clicks or so many
Yep,
buttons?
same idea. Yep. So that's one of the weaknesses of magnetic storage, is it often involves moving parts to move it around, and it's the moving parts that break. It's not so much that you lose the magnetism. And so a lot of times, if this drive fails and you want to get your data off of it, you send it to a data recovery place. What they're going to do So they're going to take it apart, and they're going to remove this little platter out of it. And they're going to stick that into a new drive mechanism with a new motor and a new wand, and then they can probably read it, because the data is probably fine. It's just the motor stuff that's 50%. Okay?
Do they sell like replacement parts, or is that too much of a risk to
Oh, well, you got to do this in a clean room environment with
sterile gloves?
Yeah, it's like a whole thing. So that's not a DIY project.
Have you ever done it yourself?
I've tried, but but like once you touch it and get the
Yeah.
fingerprint on it,
It's
just like
over.
it's
Right.
over. So
So, never mind. I answered my own question.
all right. You can also store data using secondary storage in a optically, they call it. This is usually read by a laser. So this is like CDs, DVDs, Blu-rays, and stuff like that. With the little pits and lands thing that sounds like some of you learned about in physics of light and sound. This is really cool, actually. Really high capacity. You can store a lot of information using optical storage, and it theoretically can last forever if you take care of it. There's no moving parts involved on that CD. It's like, the drive that reads the CD can fail, but the disk itself is fine. And so we used to think that those CDs that we were burning for years, like they would be around forever. But we learned that we had to be a lot more careful in the manufacturing process of those things, that it mattered what you made those disks out of, and it mattered how you stored them. Because if you store them in the sun too long, or made them out of cheap materials, so they would break, and but if you take care of them, you make them out of the right thing, like theoretically that optical storage should last forever. There's no reason it would erode really at all. So that's good. The problem is the optical storage is not very fast. It's usually pretty slow, but very reliable. I've got a lot of old projects archived on optical storage. So, but I wouldn't want to work off of an optical drive. It's just too slow. These days, we're getting a lot of good results out of solid state drives, or flash drives, as sometimes we call them. The data is stored in semiconductors in a similar way that RAM stores it. It's not as fast as RAM, though, because it's not truly random access the way RAM is. But it's much faster than magnetic or optical storage. The limitation there is that the way that the data gets stored involves a process that is limited. Like you can only write and rewrite that sector a number of times, and then it just won't do it anymore. And so, if this is a drive that you're using a lot, over time, eventually, it's just the capacity is going to shrink and shrink and shrink until it just enough sectors have gone bad that it just doesn't really work anymore. And a lot of the manufacturers will build extra drive sectors into it to account for that problem, to lengthen the life of it. So, these fail too, but they just fail in a very different way. But if you can get your data onto it and stop messing with it, it theoretically will last forever on those solid state drives. It only goes bad when you keep messing with it.
And
In
by
what
messing,
way?
you mean
Using it?
Yeah.
Okay.
Writing and rewriting and changing things.
Yeah.
If you just look at it and read it back every once in a while, it's fine. It's the rewriting over it that makes it kind of give out on you eventually.
What do you mean by rewriting? Do you mean in our own documents and
No, you've got a project or a file you've been working on, you save it to the SSD.
Yeah.
It'll be there forever.
Yeah.
But if you open it and change it and then say now save the changes on top of where the old one was, that process of rewriting onto that's what there's a clock. You can only do that so many times before it just stops doing it. And it's a lot of times. I mean, it's not like 5. It's
In that instance, would you recommend it being on the computer first and then saving those changes?
no, I mean the computer also has an SSD on it.
Yeah.
So it's not about that. It's just like there's no way around this problem.
Okay.
Like
It's just a problem that sucks.
yeah, it's just
So,
there's a lot to like about SSD, but it's not inherently any more reliable than any of the other methods. It's just a lot faster. But it will fail on you just as quickly as anything else. It just fails in a very different way.
So why don't we work off of CDs? Because it's mildly
Too slow.
slower. Well, okay, but
Too
like,
slow.
is it slow enough that it's like, this is mildly annoying, but I can get around it, or is it like impossible?
Impossible.
The CD
I don't
holds
believe
like
you. I know I asked, but I don't
CD?
believe you.
No, it's impossible.
Okay. You said it with certainty this time.
Yeah.
So.
If you had to estimate,
It's too
How
slow.
old is the CD?
if you had to estimate,
Like, is it like
How
you
slow?
can't, like,
Well, the
But
CD,
how
that
slow is
laser
too
can only be at one place at a time.
right?
Okay? And it has to read sequentially. Meaning you can't like write and rewrite it randomly. Right? You have to like you can get rewritable optical discs, but you can't like say, oh, just change this part. It's like, no, you want to save something, you're rewriting the entire disk every single time you're changing anything.
Oh.
Interesting.
Oh.
Okay.
that's
I
what you
get
needed
it
to
now.
say, and it clicked.
Yeah.
Yeah, that's scary.
Yes.
How do like RAID systems work? Because I've heard those are like used to.
What is that?
That's a way to speed a lot of drives up, or make them more reliable. So the idea is with a RAID array is like you can have multiple drives in it, and you spread the file around. So the file is like this big, and so but you've got 4 drives. So you're going to put a chunk of that file here, a chunk of that file here, a chunk of that file here, a chunk of that file here. So when you ask the computer to give you that file, it's actually going to ask for it in 4 different pieces from 4 different places, which means, however long it takes one drive to deliver a certain amount of information, like let's say it's 10 units of information, and it takes, 40 seconds for this drive to deliver 10 units of information. Well, if you split it up, then each drive is only having to deliver 1/4 of that. And therefore, the total information gets delivered faster because it wasn't all having to come from one place that is bandwidth. Okay? And so that's one of the ways that RAID works, is it's called striping. It stripes the data across multiple disks so that it's not all in one place. And therefore, the computer can get it. It says, I need this. And there's a little chip called a RAID controller that says, okay, well, that thing exists partially here, and partially here, and partially here. So you give me the part you've got, you give me the part you've got, you give me the part you've got, and then it hands it off, and the computer's like, cool. But that process is way faster than saying, you give me the whole thing, right? You give me a little bit, you give me a little bit, you give me a little bit, is way faster than you give me all of it.
But isn't that more points of failure?
Yes. And so the other thing that happens with RAID is they build in a little redundancy. So let's say we got 4 drives. We're only really effectively using 3 of them,
Oh.
because one of them includes redundancy data. And so they stripe it in a way that they store, each thing gets stored in actually 2 places. And so when it's asking for the information, it's like, okay, well, the information is divided into 3 chunks now, and each little chunk is actually stored in 2 different drives.
Oh.
And so if one drive, if it goes to the first drive, it's like, hey, give me your bit of that. It's like, I forgot it. You
You've
can
got
go,
it.
well, wait a minute, you were supposed to have it too. It's like, oh yeah, I still got it, right? And you get it that way. And so there's a little bit of redundancy, but the nice thing about that is when this drive throws a wobble, it's like, dude, I forgot. You can just pull that drive out, put an empty drive back in, and then say, all right, everybody, give the new drive all the stuff it's supposed to have. Because everybody else has a copy of everything that was supposed to be on that drive. Because this drive had a little bit of it, this drive had a little bit of it, and this drive had a little bit of it. And they can all say, all right, here's your part of this.
Well, then aren't you basically just saving everything to all of the drives all of the time? But you're just not getting
Right.
everything from
Yeah.
everyone?
Yeah.
Huh.
So it allows you the best of both worlds where, like, you get that speed boost by not having to have one thing do the whole job. But you also, you know, avoid that problem of like, well, if one goes out, they all go out, right? If I lose one piece of it, I might as well not have any of it. And you avoid that by building a little redundancy into it. That way a drive could fail and you just swap it out and it replicates the data that's supposed to be on there.
Is this like an old idea?
Oh, no.
Or this is new?
No, totally not new. I mean, it's an old idea, but it's still used. Like, we use it all the time.
Okay.
I've got a RAID array on my desk.
Old but not outdated.
Yeah. Yeah, still totally valid. There's another strategy of RAID, which is just like total redundancy RAID, which is like, I'm not looking for a performance boost here, I just want redundancy. Like, I don't ever want to lose my data ever. And so what'll happen is you will create a dual RAID array that basically has two drives in it, and everything that gets written or saved gets saved to both drives automatically.
They're cute.
Yeah. And the idea there is like each drive is a clone of the other one. Like both have the data. And when the computer talks to it talks to it like it's one thing, but there's a little chip on it that says actually when it saves the file, save it to both places. And that way if one drive fails, the dream is that they both won't fail at the same time.
However,
And usually they don't.
Usually.
So if you're like a mega corporation and your entire company is built on data, generally speaking, how many backups do you think they have?
Yeah,
A
is
lot.
that,
A
is
lot.
a
Like,
redundancy?
is that where the whole like server room comes
Yeah,
in?
they're
or
gonna
it's
have
just
have
like-
RAID arrays that have that kind of redundancy, and then they're gonna have tape backups of the RAID arrays.
of like
And then-
magnetic tape.
Yeah, and then they're gonna have off-site backups of that. They're gonna have a backup in another building in the desert of Arizona somewhere. You know, where it never rains and there's never any wind and never any floods or anything.
And you keep one at the North Pole and one at the
Yeah,
South
it's like, yeah, totally.
An
Keep one
underground.
in the Marianas Trench.
Yep.
Does a typical
it's
person
essentially
have a redundancy rate?
impossible.
Is that like common for like you?
Um,
You're just having like a regular
Ideas
rate
blowing up
of rate.
houses.
I usually, most of the time that I've done RAID arrays, I do a hybrid. I do a redundant stripe, which is like, it's a little bit of both. Like I get the extra capacity that comes with adding the drives together and the speed bump that comes with striping it, but I also build a little redundancy into the RAID design so that I can tolerate a drive failure without it being a 5-alarm fire. Like that happened this summer. One of the lights on one of my RAID drives stopped blinking. And I was a little worried that the drive had failed. And I couldn't, at the time, I didn't have the app running that could access and really interrogate that problem, because I had gotten this new computer and I had forgotten to put that app on it that could interrogate that, so I wasn't really sure what was going on. And so I was like, well, how big of a problem is this? And it was not actually that big a problem, because even if that drive had failed, like I haven't lost anything, because I can, I've got enough redundancy built into that array that I can tolerate a drive failing, but I can't necessarily tolerate two drives failing. So I'm operating without a net now, So I was a little uncomfortable. I was like, I'm okay.
For now.
Like, it's like for now, but I don't want to be in this situation for very long. And that was when I was like, it was in the summer and my little P card wasn't active, for the school. And I reached out to Jamie Woodyard and I was like, hey, if I had to buy a hard drive really quick, like, how hard would that be to do in the summer? And because like I might have a problem, and anyway, it was fine. But yes, Ken.
In the same way, can you use a RAID array with an SSD?
Oh yeah, you can build RAID arrays out of SSDs.
Really?
Totally, yeah.
How does that work when connecting it to a computer?
It usually involves some kind of enclosure box
Okay.
that you can hold multiple drives in,
Oh.
and then it interfaces with one cable into the computer.
Oh, cool.
Yeah.
Is what you were saying about like the ratio of like redundancy to the striping thing? Is that where like the levels come in?
Yeah.
Okay.
Yep. Okay. We good? All right. I don't think we've got time to get into software. Actually, you guys have had a lot of questions.
Sorry.
It's fine.
You wanna learn.
This is day one. I'm kind of scared.
Yeah, no, it's fine. I just don't want to launch into software because I don't think we've got 10 minutes and 10
Hey,
minutes
I
is
mean, we don't have a Monday meeting.
Yeah, we don't
10 minutes is not going to be enough to talk about everything I want to talk about with software. So let me just show you what I'm talking about with these RAID array ideas. Well, since you're at.
They're cute. I like them. They're like little
So
shells.
let me show you.
I love when things are black and they've got blinking lights.
I just like
Okay, so here's one called the Thunder Bay 4. This is the one I have.
The Thunder Bay.
And you can see it has 4 drives in it. Okay.
It's huge.
Oh yeah. There's a space factor here for sure.
I mean, it looks worth,
But here's what's cool about it. Like you can get this thing as big as 96 terabytes.
God.
Why would you
Um,
do that? That's like huge.
Who uses
but.
that?
So well, that's based on.
Ever again.
Unless they fail.
Which eventually they will.
I know. I'm like, you wouldn't even get close to finishing, like, completely filling up a drive before it failed.
But wait.
So you're using 4 24 terabyte drives. Okay. Yeah, Ken.
Does this also help, like, because it distributes with 4 different drivers in the same way, can it also do it with an SSD and help that, like, not overheat?
Yeah.
Solid-state drive?
Well, it's not heat. It's just like the amount of times you're writing it.
Oh, I
So, like, so yeah, you can do. Here's a Thunder Bay 4, but you can do it with. Well, no, these are all hard drive ones, but you can do your own enclosure,
Enclosure.
um,
Its own habitat.
and then you can put your own drives in it.
And feed it data.
But like, here is ooh, where is it?
But you don't want one because then it'll overheat. You want to put it in a freezer.
Okay, here's one that is based on SSD. So you can get it up to 192 terabytes,
That's
Crazy.
96 terabytes.
That's crazy.
So this thing, but this is used with SSDs. So it has, well, let's see.
I have so many questions about like what it looks like on the computer. Like, can you control what file?
No, you have no input on like what goes onto what thing. It's like that's handled by what's called the RAID controller.
Okay.
But you said you have like
But
an
does
app.
it do it optimal?
No, there's an app that lets you see how each drive is doing.
Oh, okay.
Like, is it working? Is it spinning? Is it like doing the thing? But you don't get to decide what information goes on which drive. The
Okay.
computer does that for you. But this thing is going to have a certain number of SSDs in it. So it has 12 bays. So it has 12 total SSDs in it,
Whoa.
divided up in whatever chunks it would take to get you to 96 terabytes.
Nice.
So, you know,
Could be. I don't know.
But so here's an example of, here's the app that they use. So it lets you kind of like see each drive and what it's doing.
Why do I not have one of these?
Yeah, one,
$17,000.
it's like what,
I
like how
looked up and I
common
was like,
are
that's
people,
No,
Why
free
do we not
shipping.
have this? Oh.
is it, are
It's
these like everywhere and I just don't know?
My tuition.
A lot of people use them, but like here's like something like way more reasonable.
5 gigabytes?
So
No, it's not.
I got a flash drive.
Wow, that one has a screen on it.
252.
Yeah.
Jason, how do you name your
$68
Raid Array? Do you have to
gigabytes.
pick like 4 Shakespeare
I wish I was-
characters, or do you just pick one?
Yeah, it's like a mega name for it. You know it's
Yeah.
gonna last a
Yes,
while.
on the 5
Maybe
gigabytes.
that's easier.
I have a gigabyte.
here's one that Wade has. Wade has one of these. So this is just a 2-drive RAID array. This is not that big actually. I mean it's you know.
Your hands were going like this.
No, I mean
It's not
that
big.
Yeah, it's only like, you know.
This puppy
It's
can hold
about-
so much terabytes in it.
It's about board size.
Yeah, it's like you know this maybe a little bit bigger, but then stacked.
Oh yeah.
Man, I just want to
About board.
So it's got 2 drives in it, and it just depends on how big the drive is. But you can get this up to like 48 terabytes between the two drives,
Why wouldn't?
and you can have that be either a redundant RAID where it's like duplicating the data on both drives, or you can have it be you know a extended. There's not you'd have to have 3 in order to do the striping thing. So in this case, you can either do a redundant or you can do a combined drive. So so if it was a 48 terabyte drive, that would mean you have 2 24 terabyte drives in there that gets presented to the computer as one whole thing. Or you do a redundancy, which is like if it's 2 24 terabyte drives, it looks like it's one 24 terabyte drive, but the data is getting stored in 2 places, and that way, if one drive fails, you know everything's still on the second one, and you just pull this first one out, replace it, and you're back in business.
Is that
And
what you did over the summer?
well, it turned out my drive was fine. It was just the light stopped blinking for some reason, and then it started blinking again later, and it's fine. So,
keep you on your toes.
Yeah.
I'm glad that happens to you too.
oh yeah.
It's like I had a weird medical problem and then it went away, so I'm ignoring it.
But like, just to give you, you know, a frame of reference, like, let's say you needed to replace a drive.
$2.
You know, I mean,
A lot more than $2.
an 8 terabyte drive's $200.
Yeah.
Oh,
That's actually not bad, actually.
It's reasonable.
Yeah.
8 terabytes.
Yeah.
Who are the people that need like 20 terabytes?
Yeah, like, what are you doing with that?
Oh, like video people.
Yeah.
Yeah.
Yeah,
I answered my question as I was
Do you
asking.
remember how much
what's the-
terabytes we
yeah,
had to use?
video.
How many
Oh my.
storage we had to use?
Yeah. I mean, the one I have I use for 2 things. One is I have it.
That was only a couple minutes.
I have 2 different partitions on it. One is set up as a time machine backup, so it's doing incremental backups of my computer every hour. And then the other half is an archive of like everything I've ever done in my life.
It makes me
How many
sick.
bytes is that?
It's so,
Like 16 terabytes.
yeah.
Um,
This is gonna be so much forever.
It's like my own personal archive of like all of my creative work for my entire life.
All of your stuff fits on 16 terabytes. It's like,
That's
Yeah.
crazy.
So
I was gonna ask you a question about how you felt, because me and Cal kind of got into an argument at work about saving things, like scenes on board,
Oh.
and whether or not you should keep saving everything and just like move it onto a hard drive and then keep saving things. And I was like, you can stand to delete some scenes if they're the exact same. And Cal was like, no, just save them onto a hard drive and keep moving.
Yeah, his argument was like,
And that's
I'm
what
always like, there's always like one thing on something at one point that I want that I have to go back to, and what if I deleted it?
I am always really loath to delete something if I don't have to.
Especially in the middle of something.
Yeah, it's like
Well, yeah, it was less like more like we have 60 scenes on a church console that are the exact same, you know?
Are they really? I think his argument is really like, are they the exact same?
yeah, they're not
Or
actually. You
do
know,
you-
there's little minor EQ changes or something there,
That's what Cal said.
and
We're all probably
yeah,
the
but I
same
mean,
plot.
like
I mean,
you
But he's right.
I
like
know,
you worked
I
hard on
just-
that. Why would
yeah.
you get rid of that?
Why
Like
would you
you know,
make it
if you get that same musician back in, you know, and it's like, oh, you're the person we worked with 3 years ago, and we spent a week trying to get that instrument to sound right, and we finally got it to sound right. Ooh, I still have that file. Let me just pull that channel setting out of that stored file, and then we don't have to repeat that week's of work. You know,
Yeah.
like
You
who wouldn't
also
want to do that?
CEO of data storage. What you
Well, I was gonna say, I feel like I don't have to ask you now because we just went on this whole thing
Yeah.
where you have 16 terabytes of everything you've ever done. I'm like,
Yeah.
I know the answer now.
Always keep it.
All right.
You might use it later.